Okay, section 3.2. It's called differentiability. It's a fun word to say. How many syllables does it have?
Yeah, 8, 7.
That's a lot.
A lot, yeah. Differentiability. The faster you can say it, the better double tonguer you are in band. Triple tongue. It's the reason why I can say negative so fast. It's just like a triple tongue. Negative. Okay. All right. Negative. Okay. All right, here we go. It says, the very first part says how f prime of A might fail to exist. There are 4 pictures there. Based on what you know about the existence of a derivative, it has to have the same slope from the left and the right at that point. Obviously, if you have a corner there, the slope is not the same from the left and the right. Or if you have something worse than a corner, like you see in the next picture over, they call that a cusp. There are some calculus books out there that do not distinguish between a corner and a cusp. It's a pointy thing. But you can't say it has a pointy thing non-differentiability. Call it a corner or a cusp. And if you call it a cusp when you mean a corner or vice versa, I will still give you credit. Okay, so I don't care what you call those. They're corners. They're pointy things. And if there's a pointy thing, there can be no derivative if that function has a pointy thing on it. Okay, because the slope from the left and the right is not the same. You also, and this we just now discussed that one, just a few minutes ago, if any place on the graph has a tangent line that is a vertical line, at that point there is no derivative either, because there can be no number associated with the derivative there. Vertical line slopes are undefined. You with me? So vertical lines at locations where the graph actually, for just an instant, takes on a vertical line tangent. No derivative there. Or if there is a non-removable discontinuity, meaning either a jump discontinuity or infinite discontinuity, there can be no derivative there. Because there's no tangent line you can associate with it.
If there's a point discontinuity, you still can't.
Removable discontinuity is still, well, you're right. You're absolutely right. Removable, I lied. Any discontinuity, no derivative there. No discontinuity. I mean, any discontinuity has no derivative. It has to be continuous before you can even consider the idea of derivative.
Sure.
Has to be continuous. If it is continuous, but at that point there's a corner, a pointy thing or a vertical line, is still not differentiable.
So are these all cases where you actually
Not in differentiability. Well, at the places where those things occur. Every other place on the graph is different. We good or not? You understand those 3 things? And furthermore, if from now on, if you want to say, if it says, is it differentiable at 0? You can say no. If it says explain why, you say because there's a corner there. That's all you have to say. Or there's a discontinuity there. Or there's a vertical tangent. Or there's a vertical line there. The tangent is vertical. That kind of thing. You can explain it using the geometry thing that happens there preventing it. Okay? So turn a page. Example 1 is super simple, so I'm not going to spend a long time on it. It says find all the points in the domain of this absolute value function. It's a daughter function where f is not differentiable. Find all the points in the domain means find the x values. Domain refers to x. Find the x values in this function where f is not differentiable. And that would be at 2. Just 2. Just 2. Because the vertex is at 2, 3. Do you recognize that transformation? So the x value, when it's not differentiable, is where the corner occurs. That's the vertex of this thing, which occurs at x equals 2. Yes? Yeah. Moving on. We are just going to discuss this thing of differentiability applies local linearity rather than have you do it on your calculator. Well, we might do a little bit. Actually, we are. Grab your calculator. I want you to put those 2 functions in your y equals screen. One in y1 and one in y2. Graph them on a standard screen together. Exploration 1, bottom of page 110. There are 2 functions there, an a and a b, an f and a g. Put them in your calculator. And graph them on a standard screen.
I don't like that one. I can't find the other. They're on top of each other. They're not good right now. Oh, no, what? Expression. We'll face one of them now.
This is what it looks like when they're both graphed together. And they appear to be the same thing. Except, if you look really carefully, especially you guys that have got these newer calculators with higher resolution, right here at the tops, these little squirrely things, right up here, you can see it's a bit thicker if you really look.
Yeah.
Which means they appear to be slightly different up here. Okay? Still, these places where they're a little bit fatter, a little bit thicker, right up here we're talking about, right up on the top, those are not the points of interest. Where do you suppose, based on what we've talked about so far, that we are interested in looking at this thing a little better?
Zero.
At 0, at x equals 0. Because there appears to be what there? A corner. Now,
Appears to be. Help appears.
But is there not?
It's not.
It's
Because
because
it's two square root function.
just listen. Shh, just listen. It says we already know that f is not differentiable at x equals 0. Its graph has a corner there. Graph f and zoom in at 0.01 several times. Does the corner show signs of straightening out? So what I want you to do is go to your y equals screen and turn the second one off. Do you know how to do that? Go to the equal sign and hit enter so that you're only looking at f, which is the absolute value function. I want you to hit the trace key. Cursor is not right at the corner of the function. Get it there, and then go zoom in. And you have to go zoom in and hit enter twice. Does there still appear to be a corner there after zooming in once?
Yes.
Then zoom in again. Still a corner? Zoom in again. Still a corner.
You should be on the absolute value.
Zoom in again. Still appears to be a corner. Now, look at your window. The x's only go from negative 0.04 to 0.04. That's pretty tiny, and still the graph shows, mine doesn't because I zoomed in, my cursor wasn't right where I wanted it, and it's up here. But it still appears to be a corner. And it's really tight. So, take a look at the next one. Do the same thing with g. So go to y equals, go back to a standard screen. Go back to it, and go back to zoom standard. Go to the y equals screen. Turn off the first one. Turn on the second one. And graph it. It appears like you're looking at the same thing. Take your trace. Hit trace. Get the cursor as close to that point of interest as possible and hit zoom in. Your first zoom in still appears to be a corner. Hit zoom in again. Can you see in that zoom in that it appears to be a little softer? No, it does look like that to me. Now zoom in again.
Oh, yeah.
And at the corner where there used to be a corner, it appears to be a little softer, right? More like a ballpoint pen than a needle, right? Okay. And hit zoom in again.
It's a parabola.
It appears to look parabolic. It isn't a parabola.
No.
Okay. Keep hitting zoom in. And just kind of remember how many times you had to do it until when you finally zoom in the last time, when you finally zoom in and it appears to be a straight line. How many zoom ins did you do?
Holy crap.
About how many?
Look at that mistake.
About how many zoom ins did you do to get a straight line?
Like 7.
I'm just
7 or
checking
8?
my window, so because mine doesn't zoom in very fast.
Mine's a straight line now.
Well, okay.
Straight.
Mine is 2 after about 7 or 8 zoom ins. It's straightened out. It's no longer a corner. That would not happen with your absolute value. If you do 7 or 8 of those, it would still appear to be a corner. And so, let's see. Look at your window now after that many. It's negative 1.5, and if you go back over there ways, it's times 10 to the negative 4. It's really tight screen, but it did appear to straighten out with several zoom ins, right? Does that, and what that tells us is that the second graph does have a derivative when x is 0, the first graph does not. Now, go back to a standard screen Go back to a standard screen, go into y equals, and turn on both graphs. Go back to your graph, get the cursor with your trace key on the corner, what appears to be the corner anyway, and go zoom in so that you can see them both. How long does it take before they are distinguishable? How many zoom ins where it's very, very clear they're distinguishable?
I don't think my
They're
zoom
different
is
from
zooming
mine.
as fast as everyone else's. Good thing you can just-
It took me 3.
It took me 3 too. Get a nice corner when it grabs the first one, and then it's pretty darn clear, even though they're still really close together. After 3 zoom ins, it's pretty clear that they are different from one another. And if you do a couple more zoom ins, it becomes even more clear that they are separate. But you couldn't tell that in a standard screen. They sure looked an awful lot alike. By the time I've done 4 zoom ins, it is really quite clear. What we're saying here is, what we're trying to discover here is that if you can zoom in tighter and tighter and tighter, and the graph appears to be straightening out where it used to appear to have a corner, but it appears to be straightening out, then there is a derivative there, graphically speaking. I mean, you can tell that there is. That's all we were trying to do. So when it says differentiability applies local linearity, it means if you know it's differentiable there, then it should straighten out with several zoom ins. The absolute value one never did, but the second one did. The second one did. So the second one's differentiable at 0, while the first one is not. Okay? Now, happily, your calculator knows how to calculate derivatives. Derivative values. That's pretty cool, right?
Can it find the slope generator, like the equation of the tangent?
Only if you have a CAS calculator.
I need one.
I want to teach you how your calculator thinks, though, so that when it thinks it knows what it's talking about, you will know that it doesn't. You've got to be able to be the master of your calculator, not the other way around. Don't let your calculator convince you of something that's not true just because you don't know how to think straight. So listen to me on this. Do you remember that we have this? If you have f of x, then its derivative can be found. This is one way to do it, by taking the limit as h goes to 0 of f of x plus h minus f of x over h. We've been using that for a long time. Do you remember the other one? If this is f of x, f prime of x can also be found by finding the limit as what? X approaches a of f of x minus f of a over x minus a. There is an alternative form beyond that. It's called the symmetric difference quotient. And it says this, graphically, I'm going to show you the graph of it first. If I have my classic curve like this, and I'm trying to find the derivative, let's say right here at x, then it is quite possible for me to have an x plus h out here and an x minus h, these points right here, and this distance here is h, and so is this, and they simultaneously crawl towards this, and you find this, the secant of that, the slope of that secant line, and then it moves a little farther over here as h gets smaller. You find the slope of that secant line, you move it to here and here, you find the slope of that secant line until you've gotten close enough, and close enough is an arbitrary thing. I'll show you how you can adjust that on your calculator, but until you've gotten close enough that this secant line, the calculator is going to tell you is the slope of the tangent of that curve, which if you have them crawl really, really close is going to be correct. Do you agree? But it has h's, or it has an x plus h and an x minus h, and they are crawling towards one another. And it's the slope of the secant line determined by those two. And that's what's programmed into your calculator. Why is that? Because everything in that calculator depends on a left bound, right bound, left bound, right bound, and it zeroes in. That's how it finds a zero. That's how it finds a maximum. That's how it finds a minimum. It always asks you for a left and a right bound, right? Well, without asking you that, this is how it does its derivative calculation. It has a left side and a right side, and they just move towards each other until they are close enough that it will report the slope of that secant line. And that will be the tangent curve right there. And you can make it get closer and closer and closer and closer and closer, as close as you would like. Okay? And that's called the symmetric difference quotient, and it looks like this. The limit as h approaches 0 again of f of x plus h minus f of x minus h over x plus h minus x minus h. Which is, if you can imagine that distribution, the x's will cancel out and the h's will add up. So it doesn't matter if you have two h's down here, but as h goes to 0, this is still going to get closer to 0, right? It's just got a 2h on the bottom of it.
Well, why would you put dividing by 0 on the bottom?
You just can't divide by 0. Anyway, this is what your calculator uses, and because your calculator uses this in its programming, it can lie to you and think it's telling the truth. Now let me show you the syntax for finding a derivative with your calculator. It is, and by the way, the book says that the notation, whenever you see these words or these letters in capital, enter, the author of the book is trying to get you to calculate. When it says use ender to find, it means use your calculator to calculate a derivative. In your calculator, it looks like this, enderiv. And then we'll have a parenthesis like that, and you have to put this syntax. You have to type in whatever f of x is. Not this notation, but if it's root x, you put root x there. Comma. With respect to x, because your calculator can derive things written in x with respect to something else, but not in this class.
Where's the ender of that?
Can you just hold on? Just wait, and I will tell you all these things. But this is your syntax. Comma, and you can put in here, the next thing is how accurate, how small can h be before it reports a value? And I'm thinking, no, I lied. There's two things. This next number is the x value for which you wish it to calculate it. Like, for example, I'm just going to write x value. And I'll show you one in just a minute. We'll all do it together. And then if you wanted the default error value is 0.001. So in other words, this h right here gets to be 0.001, and this one over here gets to be 0.001. When it gets that close, then it will calculate that secant line and report it as the derivative. However, if you want it closer, if you don't quite believe what the calculator is telling you and you want that to be closer, then the last thing you type in here, and it will take it, close the parenthesis, it'll do that using this 0.001 as a default. Or if you want it to be to the nearest millionth, then you will put 0.000001 right there, and it will let that thing squeeze into the millionth, or as accurate as you would like. It just can't be 0 there. Okay, so I want you all to calculate the derivative of x cubed at 2. At x equals 2. And here's how you do it. Look at example 2 so you can see his notation, and then I'll show you how to make it work out. Example 2 says compute ender. X cubed at 2, that's what that means. That's what the notation means. Which means the numerical derivative of x cubed at x equals 2. So we go like this. You go math. And they did this on purpose so that you couldn't see how to calculate a derivative until you were really looking for it. It's down. You got to go down farther. One more, and there you see. Enderiv. If you would like, instead of arrowing down to that, everybody quit. Just go back to a regular screen like this. And then go math 8. Just remember that, math 8. And it will type enderiv in your screen. And then you type this in. We'll put x cubed. So x raised to the 3rd, comma, with respect to x, that always has to go in there, comma, at 2. Close it. You have to put with respect to x in there. It goes in between so that it looks like this.
Function. And then function.
Then hit enter, and it tells you it's 12.000001.
If you want to take graph and stick that in your point graph.
Mine looks like this.
Ours are different.
Okay.
Yeah, I updated.
Yeah. That just means yours is updated.
But
Oh, okay. If yours looks like this,
Yeah.
if your calculator looks like this, D, and then down here, D box, and then it has, what does it have here?
parentheses.
And then,
it's like there's a value there.
Like stick something in there.
oh, with a
Yeah.
box?
Yeah.
Okay. So it will have another box that you have to fill in here,
No line.
and then a line, and then a,
X equals
X equals down here?
Yeah.
X equals a box, and that's all? Okay. This is with your respect to. It's the derivative with respect to x. This variable that follows the d in the denominator, that's like writing this right here. So you put an x in there. I'm going to put this in color so you can see what you fill in. And then this is the function that you're deriving. So this is where you would put x cubed. And this is where you wish to evaluate it. This is where the 2 goes. Okay? And then I think you can qualify that with a larger number. I mean, with a smaller number, but I'm not sure how that will work. Okay, so we put the x equals 2. We put these numbers in here. This is with respect to. This is the function. This is where you wish to evaluate it. This is with respect to. This is the function. This is where you wish to evaluate it. And you get the 12.000001, right? Now, do it again. Go math 8 and type in the same stuff. And I don't know how yours is going to work. We're going to try this. I want you to type in this to see if you can get it to be more accurate at the end of it. I don't know if you can just hit comma afterwards before you hit enter or what. I don't know how you do that. I'm going to have to figure that one out. What we say, x cubed, comma, with respect to x, comma, at 2, comma, 0.000001. Close it. That way you've told it you want it to be more accurate, and this time it comes out with exactly 12. Because the derivative there is 12, and it has gotten close enough now that the slope of that secant line is the derivative. Were you able to get it to qualify any better?
No, I just got 12.00.
Okay, then I'm gonna have to think about that one.
Is there a way to drop?
But if it's 12 and there's more than 3 or 4 zeros, it's making an error to round it off. Okay, yeah. Or if there's several 9s, round it off. But just do that in your own head. I'll try to figure out how to make it more accurate with that
So
operator.
instead of putting
I'm not sure how that works.
put X.
I put x at third.
Okay, do X to third, comma X.
Try this. Go back to classic view. Go to the lower
Hard to say.
down to the next screen.
Hey, mine did it.
Classic view.
I don't
Go
know.
back to.
Look at that.
Well, you still have the 2 in there.
Yeah,
Take the 2 out.
And that way,
Excellent.
if you want to, if you get to a classic view.
That's
Go
my
back
derivative.
vote, go back to pretty print or whatever they call
There
that.
you go, x,
That's right.
comma x, comma x.
If that's what you want, if that's what you're used to, then you can stay there. But you can change views. Okay, and I'll see if in yours deal, I'll see if you can increase the
What is that finding?
slope of x cubed when x is 2. The question was, what have we found? This is what we have found, folks. If you graph x cubed, it looks like this. Something like this. And what we are saying is that when x is 2, the slope of the tangent line there is pretty steep and has a slope of 12. That's what we have found. Is that on the function x cubed, when x is 2, the slope of the curve there is 12. Okay? So it's calculated the derivative.
It's above 7.
Every single point. I mean, every single soul is at the point.
That takes a while to draw.
Okay, is everybody's okay to there? Understand how to do a derivative on your calculator? Okay, now, what do you know is true about the absolute value function when x is 0? There's no derivative. Ask your calculator what it is.
That's what I did.
I'm like, graph 0.
Yeah, it's a 0.
That's not right.
It isn't right. The calculator thinks it is. Why?
Because it's that.
Because it's.
Because it uses the
Sounds like
symmetric
this.
difference quotient. I'll tell you why. And it doesn't matter how tight you zoom in, it will always tell you that the derivative there is 0. The calculator will, because of this and the way that it
I
thinks.
see. Because it's taking the points from here.
Yeah, it's doing this. It's saying, okay, here's my absolute value function. And it's saying, I'm going to figure the secant line from, and this is gonna be blown up a little bit, but let's say this was negative 0.001, and this is positive 0.001. It finds the value on the absolute value curve at this x value and at this value, and figures this, well, that was pretty crappy. Yeah.
That's okay. Funky.
And figures the slope of this line, which is 0.
As it gets smaller and smaller.
Yeah, and you can get as tight as you want. You can put as many zeros. You can get to from here to here, and it will find that the slope between these two is 0. You have to know better, because your calculator doesn't. It can't think. It just does what it's told. And what it's told in this case gives you a false answer. So you have to be careful with stuff. You got to think a little more about what you're doing rather than just blindly calculating, okay? Because the symmetric difference quotient at times, in certain circumstances, can lie to you. I want you to find the derivative of this and see if you can explain why there's a problem with this one. I'm not going to graph it. Find the derivative of f of x equals 1 over x squared at x equals 0.
Oh, I found the problem.
Yeah, same.
What does it tell you that the derivative is there?
0. Yeah,
0. Do you understand why?
Same reason. Infinite.
Same reason, yeah.
This
There is no derivative there because there's no function there. There is no function when x is 0, but it will tell you because the graph looks like this, and way up there, that's really crappy. Right through the middle there. It will find a value at negative 0.001 and positive 0.001,
Oh,
right here, and we'll find the slope between them. Now, find the derivative of this one at x equals 0.
oh my gosh.
That's kind of funny.
Oh, because it gets. Oh boy.
You can understand why, right?
Why?
What does it tell you it is?
A million.
A million.
Come on.
Which, when you understand how it figures it, makes good sense. That graph looks like this. And so it takes at right here, at 0.001, it takes one way the heck down here, and it takes one way the heck up here, and finds this slope, which is a million. And the thing's not even defined at 0. So you have to be smarter than the calculator and understand why it makes mistakes in certain circumstances because of your understanding what the graph looks like in certain circumstances. So don't be fooled and don't calculate blindly. Think. Okay. One more thing, and then one more theorem, and then we'll be done. So example 4 says, let f of x equal the natural log of x. Use Ender to graph it. Ooh, we can graph derivatives? Yes, you can. That's the next thing you gotta learn. Will you listen to me, please, for a minute? Don't try it. Just listen for a minute. Just listen for a minute. In your graphing screen, if you want to actually look at the picture of the derivative graph, remember I told you derivatives themselves are functions most of the time? Unless you're doing a line, then it's just a number. But that's a function. The constant function, which is really boring. In the y equals screen, listen carefully. If you have y1, this is what we're going to do, equals log x. Don't do this yet, just watch. And then in y2, you wish to calculate the derivative of this one and look at both of them together. Or perhaps turn this one off and look at only the derivative. That's possible. But your calculator has to have something to derive. You could type this in. So you really don't have to do y1, although I always do, because I can remember the function anyway. So in y2, you would say n deriv. And you would find it right here. When your cursor's sitting right here, you go math 8. And it will slap down a parenthesis, or it will give you the stuff. And you write in y1. Do you remember where to find that? Bars. And so if this thing is really lengthy and horrible and awful, you don't have to type it here. you can just type y1 from your vars key. And it will look back at this and say, okay, that's the function I want to derive. Comma, with respect to x, you have to do that. And where do we want this thing to evaluate it? At every x in the screen. So it's not a number that you put here. You put x again. And whatever your x min and your x max are, it's going to plot a point for every one of those pixels in the screen that you've defined for it. So you put with respect to x here. Now do it. I wanted to show you how to do it and explain what you were doing. So when you're graphing it,
X and then X.
yeah, you go y1, you type in log x. And then in 2, you type math 8 and put in y1 from the vars key, comma, x, comma, x.
Cool. If you,
Put it on a standard screen. Go to Zoom standard. You can fix the window in a minute. I mean, we're not going to be using much of it. There's your log curve. Here comes a derivative. Now, that isn't very exciting. So I am going to take out the x's on the left side of the screen and several of the y's top and bottom so I can analyze this a little more closely. What?
I have some sort of illegal nest error.
Illegal nest. Wow, I've never seen that one. Okay, go to y equals.
Illegal.
You've got it backwards.
nest.
You
That
have to
makes
put the log
sense.
x and y1 in order to derive y1.
But if
It's
I
trying to
change this
derive
Y2,
itself. That's why it's nesting.
But if I change this to Y2,
Yes, that should do it.
that's also I1. That's awesome. Good job.
Yeah.
That should work. That makes sense. And then could you just put n derivative of natural log of x? X
Yes.
X.
Yes, you could. I just always like to have the function if I can see more
Yeah.
here. But it's whatever. So I'm going to take out the left x's. No, not all of them. Maybe -1. Out to 5. And -4 to 4. That's what I'm going to do. So if I zoom in on that part that I see this graph so I can see a little more detail, just that part, and fill up the screen a little bit better. What does that graph that's graphing the derivative, by the way, the derivative graph's slower because it's got to make several calculations before it can ever put one down. What does the graph of the derivative appear to be? Is it looking like anything familiar? The positive side of 1 over x?
What I'm thinking.
Okay.
See that?
How do you check out your suspicion? How do you check that out? Go to y3 and type 1 over x and see what you get. 1 divided by x, and maybe make that one thick by going over to the left of y3 and hitting enter once so that you can see if it graphs right on top of the other. It does, but it also gives you this little piece down here that it didn't give you before, right? So is the derivative 1 over x?
Not quite.
It is, if you restrict its domain to only being x greater than 0. Why would we restrict the domain on it? I mean, can't the derivative be 1 over x?
No, because the domain of that's larger than the domain of.
Right. Your domain of your derivative can never be bigger than the domain of your function, ever. Okay, so we would say this, if by what our investigation shows, we're saying that if f of x is equal to the natural log of x, then f prime of x is equal to 1 over x, so long as x is strictly greater than 0.
Can the derivative's domain be the same, equal to the?
Oh, yes, and it is quite often. It can also be less than, but it can never be more than. So you'll have to restrict the domain. We believe that it's 1 over x, but only the right side of it. And it turns out, which we will prove later, it turns out that that's true. The derivative of log x is 1 over x. For x greater than 0. You have to pay attention to that. Okay, so I want you to consider this last thing, this theorem right here. At the top of page 113, and then we won't do any, it's not like I'm quitting, we're just not going to do the rest of the lecture. We're going to stop with theorem 1. Think about what I'm saying as soon as you're done writing things down so you can listen, because this takes a little bit of brain effort.
So, is also 1 over x, like the derivative of 1 over x, is that also natural log of x? Or they not swap?
No, you can't switch them back and forth. No.
Okay.
Nope. Turns out that the derivative of 1 over x is negative 1 over x squared. See all these things later. I mean, we could use the difference quotient, you know, the limit of the difference quotient to find the derivative of this, but it won't have anything to do with this. Okay. Now, if I asked you, find me a function whose derivative is 1 over x, you would say log x.
I'm so confused. How could you find that natural log of x, this derivative was 1 over x?
It's coming.
Okay.
You gotta wait. And it's gonna be several sections later, way
How
after,
did you find
it's
that
gonna be
out?
way after harvest. It's like the 9th section of this.
How did you know that just from graphing it though?
Because when we asked the calculator to graph the derivative, and then we graphed 1 over x, they graphed right on top of each other.
So
That was
it's
our only
kind of-
evidence at this point.
Yes.
We'll prove it later algebraically, but for right now, graphically speaking, we are convinced. And we have not been fooled. It's true.
Okay.
It is true. We'll show it later. Okay? Now think about this with me. This is the last thing I want you to think about. If I guarantee for you, and any function that you can think of, if I guarantee that it has a derivative at a, does that mean it's continuous there?
Yeah.
If I tell you it's differentiable,
Yeah.
does that mean it's continuous there?
Yeah.
Okay. If I tell you that a function is continuous at a, does that mean it's differentiable there?
No.
Okay, so what we say is differentiability implies continuity. But continuity does not necessarily imply differentiability. So it's a theorem that reads forward correctly one way, and then when you reverse it or do its converse is not necessarily true. So it's not biconditional. Remember these words from geometry?
Yeah.
So differentiability implies continuity is not a biconditional statement. If it's differentiable, then it's continuous, but that's the only direction you can go with it. Just because it's continuous does not mean it's differentiable, so you can't reverse that. So that's what it's saying in theorem 1. Differentiability implies continuity. If f has a derivative at x equals a, then f is continuous at x equals a. And that's all you could say. You cannot reverse that and have a truth. Okay, now I'm done. Hope you like that. See you later. Now, do you have any